Hello and welcome to T3 Day 9 of Honors Precalculus. We're going to continue talking about conic sections, but we're going to define them with polar functions. Now, it seems like this might make it more complicated, and it does look more complicated, but we're going to set it up so that it's actually super helpful. And we're dealing with three different shapes that we've already seen before. Keep in mind we're dealing with ellipses, parabolas, and hyperbolas. And the way we're going to define them now is we're going to define a conic section as the set of all points in a plane whose distances from a particular point, the focus, and a particular line, the directrix, things we've seen before, have a constant ratio, We call the constant ratio the eccentricity. So this is the eccentricity in polar defined conic sections. So what's going on here is we have our focus, we have our directrix, which is this line right here, and we're looking at the ratio from here, which is from the focus to a certain point, any point, and it's constant when you compare it to that distance right there. The key thing there is that's a 90-degree angle right there. That's perpendicular. So what's going on here is we're defining the eccentricity to be PF, which is that green distance, over PD, which is the yellow distance, which also means if you multiply both sides by PD, you get PF is equal to the eccentricity times PD. The reason this is really cool when we do this with polar functions is that it allows us to define our conic sections like this. It will be a hyperbola if the eccentricity is greater than 1. It'll be a parabola if the eccentricity is 1, and it'll be an ellipse if it's between 0 and 1, and it'll be a circle if the eccentricity is 1. So you can find this eccentricity, and then it'll tell you what conic section you're dealing with. So again, this is what it looks like here. If the eccentricity is less than 1, right here, if it's less than 1, so that would be this distance, PF to PD, that fraction. If it's less than 1, then you're dealing with an ellipse. And what's going on here, you'll notice, is that we're putting the focal point at the origin. That's one thing we're going to do to make this really, really nice. The math is way better this way. And then if it's equal, so if this distance is equal to this distance, then you're dealing with a parabola right there, a parabola. And then if it's greater than 1, so you're dealing with, again, this distance over this. You can kind of see how it comes out to be greater than 1. You're dealing with a hyperbola. So we now can move on. So kind of what's the point? Where do we use this? Well, astronomers use this a whole bunch because there's lots of things that move according to these arcs, and it's much easier to define them this way. So what we're going to do to make things easier is we're going to put the focus at the origin. The focus is going to be at the origin, which is going to be super helpful. It simplifies things a great deal. And our directrix to simplify things is just going to be x equals k. That's going to be the vertical line. We're going to simplify things, and it helps us do some math, makes it a little bit easier to do, and we'll take whatever we can get. What this means, if this right here is a right angle right there, what that means is this distance right here, this distance from here to here, that distance right there is going to be equal to r cosine of theta, just by the definition of trig. So that's that x distance. So this x coordinate right there is r cosine theta. So what that means is that this distance right here, that distance right there, furthest side is k, and this side is r cosine theta. This distance right here is going to be k minus r cosine theta. That distance is k minus r cosine theta. So if we look at a few more definitions here, PF, which is this distance right here, we're defining that to be r. I'm just calling that r right there. And PD, which is this distance right here, we know is going to be k minus r cosine theta. So we have those two distances right there. So the eccentricity is PF. Again, PF is the green right there, and then you have PD. So we have a little bit more information to work with. What this tells us then is that the PF value is r, we're calling it r, and PD is k minus r cosine theta. So what does that tell us? It tells us that E is equal to r over k minus r cosine theta. And you might remember that polar functions are defined as r theta, each point. So each point is the distance from the origin and then the angle from the positive x-axis. So let's do some rearranging here. So what we're going to do is first we're going to cross multiply. So what we'll do here is I'll make this e over 1. So when I cross multiply, I end up with e times k minus r cosine theta equals r. I'm going to distribute, so I get e times k minus e times r cosine theta is equal to r. So what that means is that ek is equal to r plus er cosine theta. It's kind of fun to say all this. So what that means ultimately is that ek, we can factor out an r, is equal to 1 plus e cosine theta. Remember, this is eccentricity, not the number e. So we divide both sides by this, and we end up with r is equal to e times k over, it's e times k over 1 plus e cosine theta, right there. And this is going to be with one focus at origin. That's really important here. The way this is set up is that one focus is at the origin, and the eccentricity is equal to e. So what we did there is we now have a function where you plug in, you get r out with theta. So these are going to be known things. E and k are going to be known, and then you have r and theta. So this is a polar function. This is a polar function. So then you have all these different forms for the 4 standard orientations of a conic in polar plane. And what you end up with, keep in mind that all of these are the same right here. Sorry, let me get a better highlighter here. The right-hand side of each of these is the same in each case. KE, we did it as EK, kind of like it in alphabetical order right here. These are the 4 different ways here that it could be done. It could be done like that. So how do we write an equation given a focus is at the pole? We're going to write a polar equation here, so it's r theta. The key here is that this eccentricity is 3/5. That tells us that this, because it's less than 1, is going to be an ellipse, and its directrix is x equals 2. So we know the equation already is ke. We do ek, it's the same thing because its multiplication is 1 plus e cosine theta. So what you literally get to do is the e is 3/5, so we plug in 3/5 right there, and we know the k value. It tells us the k value is 2. It's just a plug-in here. So what do we end up with here? We r equals k, so it's going to be 2 times 3/5 all over 1 plus 3/5 cosine theta. And you can simplify this a little bit if you wanted to. I like multiplying it by 5 over 5. That's just a form of 1. And the reason that's nice is that it cancels the 5s right there, and then this multiplies there, and this turns into 5. So what you end up with is r is equal to 6 over 5 plus 3 cosine theta. And now if you want to graph this, you can use Desmos to graph this. You can plug that into Desmos and it'll give you a really cool ellipse. And remember, one focus is going to be at the origin. One focus is going to be at the origin. I also recommend trying to graph this on your calculator, but here is the equation you'll use. So I left what this looks like in there, and this tells you right here that this, because it's greater than 1, is going to be hyperbola. And then it tells you that the k value here is 4. So that tells you k is equal to 4 and e is equal to that. So we know the function is ek or ke, you can do either one, 1 plus e sine of theta. This is where I need to go back and show you something. If it's up and down, there is one difference here. It becomes sine. If it's vertical, it becomes sine. Sorry, side to side is cosine. I forgot to mention that. And up and down is sine right there. So that's why it's 1 minus e sine theta. So if it's vertical, it's sine. If it's side to side, it's cosine. And the reason we know this one is vertical is because the directrix is y equals 4. So if the directrix is this, it's going to have to go up and down. If it's x equals something, the directrix is vertical, so it has to go side to side. So here it's just fill in the blank right here. So you end up with r is equal to 3/2 times 4 all over 1 plus 3/2 sine of theta. And similar to what I did before, I'm going to multiply by 2 over 2 just to get rid of the fractions. So you end up with r is equal to 12 over 2 plus 3 sine theta. And then you can use Desmos or your calculator to check. It looks just like this. Y equals 4 is right here. It's pretty cool. So remember, the foci is right there. It's a pretty neat graph. So what do we do here if we're given the equation and we need to find the eccentricity and the type of conic in the directrix? Well, let's put it into the right form. The right form up here, you'll remember that up at the top we need to change it. It's e times k up top. but the key thing here is that it needs to be 1 right there. So how do we turn 2 into 1? We multiply the top and the bottom by 1, which is going to be 1/2 in each case, because when we multiply these two things together, we get 1. This is just a form of 1, so it doesn't change the overall value. So what we end up with, r is equal to 6 times 1/2 over 2 times 1/2. I'm doing out a kind of an extra step, 3 times 1/2 times cosine of theta, like this. So when you simplify this, you end up with 3 over 1 plus 3/2 cosine theta, like that. And we know, therefore, that this number right here, the one before, that has to be the e value. That's the e value by definition of our formula. 3/2 is greater than 1, therefore it's a hyperbola, right? And therefore we also know that the top here, this right here, has to be ek. So ek is equal to 3, but we know that e is equal to 3/2. So we have 3/2 times k is equal to 3. So k is equal to 3 times 2/3, which is 2. So in this case, k is equal to 2. So we found all that. The directrix is k equals 2. And because it's cosine, it's side to side, so x is equal to 2 is where the directrix is. And again, the focus is right there. So just to recap, our general form is this if it's going from side to side, and the only thing that changes is it goes vertical if that's sine right there. E is the eccentricity, and that tells us what type of conic section we're dealing with, which is going to be right down here. So if E is, if E, eccentricity, sorry, it's right here. If E is greater than 1, it's a hyperbola. If it's equal to 1, it's a parabola. It's an ellipse if it equals 1, and it's a circle if it's 0.